I love playing guitar, but there are a few things about the way it sounds that I've never quite understood. Most guitar players know that if you pick the strings closer to the bridge, you get a much brighter, kind of clangy sound. But if you pick the strings closer to the middle of the string, you get a much warmer, bell-like, chimey sound. The second thing I've really never understood is why, if you position a pickup, that's what picks up the sound of the string, close to the bridge, you get a much brighter, more attacking kind of sound. But if you position that same pickup toward the neck, you get a much warmer kind of sound. The last thing that most people don't really notice about the guitar, if you pick a string, sometimes you'll hear the primary note you've been playing decay away and a different note takes its place. Let's try that with the G string. It's very subtle, but you can hear it a little bit. When I pick the string, you'll at first hear the G note, but as it decays, you'll start to hear a higher pitched, different note. This one's very subtle, it's a little bit hard to hear. I thought I'd try to explain some of these things using physics today, primarily structural vibrations, using some terminology and some phenomena that you may or may not have heard about. So let's get to it.
The first thing I'll do is write down the final answer. This equation represents how the string moves as it vibrates. I'll explain what each part of this equation means later on, but for now I'll just say that each term answers a different question about the string. We can answer three basic questions. How does the string vibrate in time and space? How is the string excited or plucked? And how does the string lose energy or decay over time? Let's first answer how the string vibrates, since this is where most of the physics of the problem comes in. I like to think of guitar strings like slender beams that are held in place at both ends. The ends of the string are free to wiggle and rotate at the nut and bridge, they just can't slide back and forth. Physically speaking, this means that we have a zero displacement and a zero moment boundary condition at both ends. Euler-Bernoulli beam theory tells us that if a beam's vibrational amplitude is small, like our guitar strings, then the string's acceleration is proportional to its displacement. This is why the string tries to go back to being straight when it is pulled to one side. Since we are simply plucking the string rather than bowing it like a violin, we don't have to worry about any external force on the string. After a little math where we apply the boundary conditions, we find out that the string vibrates like a sine wave in time, and the shape of the string also looks like a sine wave. But it doesn't just vibrate like one sine wave, it vibrates like the sum of an infinite number of sine waves at the same time, each with a different frequency and wavelength. Musically, these frequencies are the harmonics of the fundamental note. The sine waves that make up the shape of the string are called mode shapes, since each represent a mode of vibration. On the left of this visualization are the first four mode shapes shown separately. Notice that the modes with more peaks vibrate faster than those with fewer peaks. We call these high-frequency modes with more peaks high-order modes. If we follow the height of the blue dot as the mode shapes vibrate and plot it on the right, we can see that the shape that is drawn is a sine wave, similar to the mode shapes. The mode shapes on the left are what we see when we pluck a string, and the tracings on the right are what we hear. When a real string is plucked, we hear and see all of these modes at the same time. If we move the blue dot to the middle of the string, notice what happens. The second and fourth modes stop vibrating while the first and third modes yield a higher amplitude tracing. This shows that where we measure the string with a pickup can have a great effect on how much of each mode we hear. Now that we know how the string vibrates, let's see how we can account for plucking the string. Plucking a string is the same as pulling it a short distance and letting it go. Notice that when I pull on this loose guitar string, the string's shape looks like two straight lines going from my finger to either end of the string. This isn't exactly the shape, since the string bends smoothly around my finger, but it's close enough for me. However, we just said that the string can only take the shape of its mode shapes while vibrating. How can this triangular shape be made of smooth mode shapes? In the early 19th century, Joseph Fourier discovered that any function can be built out of sinusoids. In this case, the shape of the string when it's plucked is the function, and we can build it out of the mode shapes, which are sinusoids. In this visual, we can see that adding together a specific amount of each mode shape creates a shape similar to the pulled string. An infinite number of mode shapes would create the exact same shape. This table shows how much of each mode is used, with bigger numbers meaning more of that mode is used. The larger the weight, the louder the mode will be. Notice that the first mode has the biggest contribution, while the higher order modes have less of an effect. This tells us that when the string is first plucked, we mostly hear the first mode, which corresponds to the named note of the string. The other modes contribute to the overall timbre as harmonics. The mode shapes still build to create the string's shape when the string is plucked at its center. Notice that the first mode still has the most contribution, but now the even number modes have no effect at all. This is why picking the string near the center gives a warmer sound. The harmonics have less of an influence, so we hear more of the fundamental note. Where we pluck the string matters. This is what our string's vibration looks like using the first 6 mode shapes and picking it near the right-hand side. The string vibrates back and forth and looks convincing so far, but it will continue to vibrate forever without ever getting quieter. For that to happen, we must consider energy loss. Energy loss in vibrating systems is due to a phenomenon called damping. Damping can come from several sources, and in general, the amount of damping depends on the vibrational frequency. For our string, damping comes from friction between the string and its endpoints at the bridge and nut, friction between the string's core and its wrapping for wound strings, and even resistance from the surrounding air, which causes high-frequency modes to decay quickly. Damping can be complicated to model mathematically, but it usually causes exponential decay. The mode shapes we derived before are orthogonal, meaning the vibration of one mode does not affect the vibration of the others. This means that each mode decays at a different rate based on its frequency. This has implications for our guitar string. Typically, the lowest frequency modes start out loud and decay slowly, while the higher frequency modes start out quiet and decay quickly. This is what causes the sharp attack sound when a string is first plucked. Since the decay is exponential, the first 2 or 3 modes will typically decay to around the same level after a long period of time. This is why we start to hear a different note emerge after plucking a string and waiting a while. If we include damping effects, the string's amplitude decays. Since all the modes decay at different rates, we also see the overall shape of the string change as it dies out, and we get a more and more simple vibration shape. Now let's put it all together. The way the string vibrates in time and space depends essentially on 4 factors. The way the string is plucked affects how much of each mode is present at first. The damping decides how fast each mode decays. The mode shapes and position of the pickup together decide how much of each harmonic you'll hear. And physical theory itself tells us that the sound wave we hear must be a sum of sine waves at different frequencies. The sound wave from a physical string can never be a square, triangle, or saw wave. I've built a synthesizer based on the equation for a vibrating string. There are 4 controls based on the 4 parameters I discussed before. We can adjust where the string is plucked, where we place the pickup, the damping of the first 10 modes, and since this is a synthesizer and not a physical string, we can generate a sine wave, square wave, triangle wave, or a sawtooth wave as the waveform. The attack knob is just an effect that allows for volume swells, so I'll turn that off for this demonstration. First, I'll set up a fairly standard guitar string configuration. I'll adjust the pickup location so that it's near the bridge, and I'll pluck the string at around the same position. Now I'll try plucking the string closer to the middle of the string. Just like the real string, we get a warmer, more bell-like sound when we pluck at the string's center. Now I'll try plucking near the endpoint again, but I'll measure the string closer to the middle, which will again give a warmer, less aggressive sound. For the last demonstration, I'll move the excitation and pickup locations to the same location again, and I'll adjust the damping of each mode. I'll turn up the damping of the higher order modes, which will cause them to decay faster. Then I'll turn down the damping of the third mode. You can now hear the fundamental frequency decay away while another note, corresponding to the third mode, takes its place. Our model accounts for all the phenomena I described at the beginning.